Hello students, I am Dr. M.S. Sawan. Today I am introducing you another part of the data transmission media. This transmission media we already know is supported by physical layer of the network operating system. Many transmission media are available for transmission of data from source machine to the destination machine. In order to increase the distance of communication, we have to use some signal encoding techniques or signal coding techniques called as channel coding techniques in the physical layer of the network operating system. And today we will discuss these channel encoding techniques. Both analog and digital information can be encoded as either analog or digital signals. The simplest form of digital encoding technique is the digital data digital signals. Next encoding technique is digital data analog signals, in which the modem converts digital data to an analog signal so that it can be transmitted over a analog links. The next encoding system is analog data digital signals, in which analog data such as voice and video are digitized for the transmission over the digital links. Then analog data analog signals. Analog data are modulated by the carrier frequency to produce the analog signal in different frequency band, and this signal is transmitted over the analog transmission links. Figure shows the process involved in this. For digital signaling, a data source J of t, which may be either digital or analog, is encoded into digital signal X of t. The basis for analog signaling is continuous constant frequency FC signal known as a carrier signal. Data may be transmitted using carrier signal by modulation, which is the process of encoding source data into a carrier signal. All modulation techniques involve operation on a one or more of the three fundamental frequency domain parameters. These parameters are amplitude, frequency, and phase. If input signal m of t may be analog or digital and is called the modulating signal, and the result of modulating the carrier is called as modulated signal S of t. Then we will see the first technique, digital data digital signal. Encoding digital data to the digital signals is very popular signaling technique or signal encoding technique. We know that a digital signal is a sequence of discrete discontinuous voltage pulses as shown in the figure. Each pulse is a signal element. Binary data are transmitted by encoding data into signal elements. In simplest case, there is a one-to-one corresponds between bits and signal elements. More complex encoding schemes are used to improve performance by altering the spectrum of the signal and providing synchronization capabilities. In general, the equipment for encoding digital data into digital signal is less complex and less expensive than the digital to analog modulation equipments. Then we'll see meaning of some terms, or we'll define some terms. For example, unipolar is defined as all signal elements have the same signs. Then polar, one logical state represented by positive voltage and other by negative voltage. Then data rate, the rate of transmission in bits per second. Then duration or length of the bit is the time taken for a transmitter to emit a bit. Modulation rate, the rate at which the signal level changes. This is also be called as baud rate. It depends upon which digital encoding technique is used. The next term is mark and space. That is the mark frequency and space frequency. Marks frequency and space frequency are used to represent binary 1 and binary 0 respectively. Then interpretation of signals. The task involved in the interpretation of the signals at the receiver requires or can be summarized as: first, the receiver must know the timing of each bit, then how at what instant the bit starts or begins and at what instant bit ends. The second, the receiver must determine whether the signal level for each bit position is high or low. These tasks can be performed by sampling each bit position in the middle of interval and comparing this value to the threshold value. This can be done because of noise and other impairments. There will be errors. There are three factors which are important in signal interpretation, and these factors are signal to noise ratio, data rate, and the bandwidth. An increase in the data rate increases the bit error rate. An increase in the signal to noise ratio decreases the bit error rate. An increase in bandwidth allows an increase in the bit rate. There is another factor that can be used to improve performance, and that is the encoding scheme. The encoding scheme is simply the mapping from data bits to the signal elements. A variety of approaches have been developed. We will see one by one. Before considering different encoding schemes, we will see some points which are used for comparison of encoding techniques, or based on which comparison of encoding schemes is done. First point is signal spectrum, which includes lack of high frequencies, required bandwidth, lack of DC component, whether AC coupling is allowed, then whether isolation is provided or not, then whether power is concentrated in the middle of the bandwidth or not. Based on this, we can able to compare the encoding schemes. Another point of comparison is clocking. That is the need of synchronization, then use of external clock or sync mechanism for synchronization purpose. These things are also used for comparing the encoding schemes. Next one is error detection mechanisms, which are different in different encoding schemes. Then signal interference and noise immunity capacities are again different in different encoding schemes. Some codes are better than others. Then cost and complexity is also different for different encoding schemes. Definitely higher signal rate leads to higher costs, and the some codes requires signal rate greater than the data rate. And now we will switch towards encoding schemes. Different encoding schemes are shown in this figure, that are NRZL, that is non-return to zero level. Next one is NRZI, that is non-return to zero inverted. Bipolar AMI, AMI stands for alternate mark inversion. Then pseudo ternary code, Manchester code, and differential Manchester code. First, we will see first code, that is NRZL. The most common and easiest way to transmit digital signal is to use two different voltage levels for the two binary digits. Codes that follow this strategy share the property that the voltage level is constant during the 1 bit interval and there is no transition, that is no return to zero voltage level. Absence of voltage used to represent binary 0 and constant positive voltage is used to represent binary 1. More commonly, a negative voltage represents one binary value and the positive voltage represents other. This is known as non-return to zero level, that is non-return to zero inverted. Non-return to zero is inverted is a variation of NRZ. As with NRZL, NRZI maintains a constant voltage pulse for the duration of bit time. The data bits are encoded as a presence or absence of signal transition at the beginning of the bit time. A transition low to high or high to low at the beginning of the bit time denotes a binary 1. No transition indicates the binary 0. NRZI is an example of differential encoding. In differential encoding, the information to be transmitted is represented in terms of changes between successive signal elements rather than the signal elements themselves. The encoding of current bit is determined as follows. If the current bit is a binary 0, then signal bit is encoded with the same signal as the preceding bit. If the current bit is binary 1, then the current bit is encoded with a different signal than the preceding bit. One benefit of differential coding is that it may be more reliable to detect a transition in presence of noise than to compare a value to a threshold. Another benefit is that with a complex transition layout, it is easy to lose the sense of the polarity of the signal. Then NRZ, pros and cons. The NRZ codes are the easiest to engineers and in addition makes efficient use of bandwidth. Most of the energy in NRZ and NRZI signals is in between DC and half the bit rate. The main limitation of NRZ signals are the presence of DC component and the lack of synchronization capacity or capability. Consider that with a long string of ones or zeros for NRZL or a long string of zeros for NRZI, the output is constant voltage over a long period of time. Under these circumstances, only drift between the clocks of transmitter and receiver will result in loss of synchronization between the two. Because of their simplicity and relatively low frequency response characteristics, NRZ codes are commonly used for digital magnetic recording. However, their limitations make these codes unattractive for signal transmission applications. Then multi-level binary bipolar AMI. A category of encoding technique known as multi-level binary addresses some of the deficiencies of the NRZ codes. These codes use more than two signal levels. In bipolar AMI scheme, a binary 0 is represented by no line signal and the binary 1 is represented by positive or negative pulse. Binary 1 pulses must alternate in polarity. There are several advantages of this approach. First is there will be no loss of synchronization if a long string of ones occurs. Each one introduces a transition and the receiver can synchronize on that transition. A long string of zeros would still a problem. Second, because of the one signals alternate in voltage form, positive to negative, there is no need, there is no DC component. The bandwidth of the resulting signal is considered less than the bandwidth of the NRZ. Finally, the pulse alteration property provides the simple means of error detection. Any isolated error, whether it deletes a pulse or adds the pulse, causes a violation to this property. Then, multi-level binary pseudo-ternary code. The comments on bipolar AMI or information of bipolar AMI is also applied to the pseudo-ternary code. In this case, binary 1 is represented by absence of the line signal and the binary 0 is represented by alternating positive and negative pulses. There is no particular advantage of this scheme over a previous scheme, that is the bipolar AMI scheme. Each scheme is a basis of some applications. Then multi-level binary issues. Although a degree of synchronization is provided with these codes, a long string of zeros in the case of AMI or ones in the case of pseudo-ternary still presents a problem. Several techniques have been used to address this deficiency. One approach is to insert addition bits that force the transitions. This technique is used in ISDN. ISDN means Integrated Services and Digital Networks. In this network, this technique is used for relatively low data rate transmission. Of course, at high data rate, this scheme is expensive because at high data rate, it results in an increase in transmission rate. To deal with this problem, at the high data rates, a technique that involves a scrambling is used. Thus, with suitable modification, multi-level binary schemes overcome a problem of NRZ codes. Of course, as with any engineering design decision, there is a trade-off. With multi-level binary encoding, the line signal may take on one of the three levels, but each signal element, which could represent log 3 to the base 2 is equal to 1.58 bits of information, bears only 1 bit of information. Since the receiver of multi-level binary signals has to distinguish between three levels, plus amplitude, minus amplitude, and zero amplitude, that is, or because of this, the multi-level binary signal requires approximately 3 dB more signal power than the two-valued signal for the same probability of bit error. That is, in other words, the bit error rate for NRZ code at a given signal to noise ratio is significantly less than that of the multi-level binary coding technique. Then we will see Manchester coding. The Manchester coding is shown in the slide. In the Manchester code, or there is another set of coding technique grouped under the term biphase that overcomes the limitations of NRZ codes. And the two such coding techniques are Manchester and differential Manchester codings. In the Manchester code, there is a transition at the middle of each bit period. The mid-bit transition serves as a clocking mechanism and also as a data. Low to high transition represents a logic 1 and low to high transition represents logic 1 and high to low transition represents logic 0. Biphase codes are popular techniques for data transmission. The more common Manchester code has been specified for IEEE 802.3 standard, that is Ethernet standard. It is also be specified for baseband coaxial cable, and it is also well defined code for transmission over twisted pair bus, which are used in different LAN systems. Then differential Manchester coding. This coding concept is also shown in the figure. In differential Manchester coding, the midpoint transition is used only to provide clocking. The encoding of 0 is represented by presence of transition at the beginning of bit period, and 1 is represented by the absence of transition at the beginning of bit period. Differential Manchester has a added advantage of employing differential encoding. Differential Manchester has been specified for application, that is IEEE 802.5 token ring LAN, in which the shielded twisted pair is used as a transmission media. Then biphase coding schemes, pros and cons. All the biphase techniques requires at least one transition per bit time and may have as many as 2 transitions. Thus, the maximum modulation rate is twice that of the NRZ. This means that the bandwidth required is correspondingly greater. The bandwidth for biphase codes is reasonably narrow and contains no DC component. However, it is wider than the bandwidth for the multi-level binary codes. On the other hand, the biphase schemes have several advantages. First advantage is synchronization, because there is a predictable transition during each bit time. The receiver can synchronize on that transition. So such codes are called as self-clocking codes. Second advantage is no DC component. Third advantage is the error detection. The absence of the expected transition can be used to detect errors. Noise on the line would have to invert both the signals before and after the expected transition to cause an undetected error. Then next form of encoding scheme is digital data analog signal. Now we turn towards the case of transmitting digital data using analog signals. The most familiar use of this transformation is for transmitting digital data over the public telephone network. The telephone network was designed to receive, switch, and transmit signals in the voice frequency range, that is from 300 to 3400 Hz. It is not at present suitable for handling digital signals from the subscriber locations. Although this is a beginning to change. Thus, digital devices are attached to the network via modem. Modem stands for modulator, demodulator. And this modem converts the digital data to analog signals and vice versa. As stated, modulation involves operation on one or more of the 3 characteristics of the carrier signal: amplitude, frequency, and phase. Accordingly, there are 3 basic encoding or modulation techniques for the transforming digital data onto analog signals. ASK, that is amplitude shift keying; FSK, that is frequency shift keying; and PSK, that is phase shift keying. In all these cases, the resulting signal occupies a bandwidth centered on the carrier frequency. So figure shows these modulation techniques. First bit stream is shown, then ASK signal, BFSK signal and BPSK signal. In ASK, the two binary values are represented by two different amplitudes of the carrier frequency. One amplitude is for logic 0 and another amplitude is for representation of logic 1. Mostly absence of carrier is represented by logic 0 and presence of the carrier is represented by logic 1. This ASK technique is used modulation technique on a voice grid lines, which is used for transmission of data up to rate of 1200 bits per second, that is 1200 bits per second. This ASK technique is very popular to transmit the digital data over the optical fibers, where one signal element is represented by light pulse while the another signal element is represented by absence of the light pulse. Then most common form of FSK is binary FSK, BFSK, in which the two binary values are represented by two different frequencies near the carrier frequency as shown in the figure B. The variant of the BFSK is called as MFSK, that is the multiple FSK. Then in last figure, that is PSK is shown, BPSK is shown. In PSK, the phase of the carrier signal is shifted to the representation of the data or shifted for representation of the data. The simplest scheme uses two phases to represent the two binary digits, which is shown in the figure C. An alternative form of two-level PSK is differential PSK, that is DPSK. In this scheme, a binary 0. In this scheme, the binary 0 is represented by sending a signal burst of the same phase as the previous signal burst sent. A binary 1 is represented by sending the signal burst of the opposite phase to the preceding one. This term differential refers to the fact that the phase shift is with reference to the previous bit transmitted rather than some constant reference signal. A differential encoding or in differential coding, the symbols or the informations to be transmitted is represented in terms of changes between the successive data symbols rather than the signal elements themselves. Differential PSK avoids the requirement for an accurate local oscillator phase at the receiver, that is matched with the transmitter. As long as the preceding phase is received correctly, the phase reference is accurate. Other variants of the phase shift keying techniques are QPSK, OQPSK, that is orthogonal quadrature phase shift keying, OQPSK. Then quadrature amplitude modulation. Quadrature amplitude modulation, QAM, is a popular analog signaling technique that is used in symmetric digital subscriber lines. Asymmetric digital subscriber lines, that is ADSL lines. And in some wireless standards, also QAM is used. The modulation technique is a combination of ASK and PSK. QAM can also be considered a logical extension of QPSK. QAM takes the advantage of fact that it is possible to send two different signals simultaneously on the same carrier by using the two copies of the same carrier. For example, you take a signal at a phase shift of 90-degree. Then original carrier, over a original carrier you can send one signal, and over a 90-degree phase shifted carrier you can able to send another signal. That is, the two independent signals are simultaneously transmitted over the same medium. At the receiver, the two signals are demodulated and the results combined to produce the original binary input. Then we will see another signaling technique, that is analog data digital signal. The device used for converting analog data into digital for the transmission and subsequently receiving the original analog data from a digital is known as codec, that is the coder decoder. The two principal techniques used in codecs are pulse code modulation and delta modulation. The next coding technique is analog data, analog signals. Analog data can be modulated by carrier frequency to produce an analog signal in different frequency bands. These things can be utilized on an analog transmission system. That means here, analog data modulates the carrier frequency and produces the analog signal, and this analog signal is transmitted over the analog links. The basic techniques are amplitude modulation, frequency modulation, and phase modulation. Modulation has been defined as a process of combining an input signal m of t and the carrier frequency f of fc to produce a signal s of t, whose bandwidth is centered on carrier frequency. For digital data, the motivation for modulation should be clear. When only analog transmission facilities are available, modulation is required to convert the digital data to analog form. The motivation when the data are already analog is less clear. After all, voice signals are transmitted over a telephone lines at their original spectrum. There are two principal reasons for analog modulation of analog signals. A higher frequency can be used for effective transmission, since for unguided transmission it is virtually impossible to transmit baseband signals. And modulation permits frequency division multiplexing. Then analog modulation techniques. Amplitude modulation, frequency modulation, and phase modulation, which are shown in the figure. Amplitude modulation, AM, is the simplest modulation technique. It involves the multiplication of input signal by the carrier FC. The spectrum consists of original carrier plus spectrum of the input signal translated to FC. The portion of the spectrum having frequency greater than FC is the upper sideband, and the portion of the spectrum having frequency smaller than the carrier frequency is the lower sideband. Both upper and lower sidebands are the replicas of original spectrum. A popular variant of the AM, known as single sideband, takes the advantage of sending the only one sideband, which eliminates the bandwidth requirements, or which reduces the bandwidth requirement. The frequency modulation and phase modulation are special cases of angle modulation. For phase modulation, the phase is proportional to, or variation in the phase is proportional to, the modulating signal amplitude. For frequency modulation, which is the derivative of the phase modulation, in which the phase is proportional to the modulating signal, but that is, in frequency modulation, frequency of modulated signal varies in accordance with the amplitude of the modulating signal. Both AM, but as with AM, both FM and PM results in a signal whose bandwidth is centered at the carrier frequency. But the magnitude of that bandwidth is very different because FM and PM requires greater bandwidth than AM. So these are the different signaling techniques which are widely used in the physical layer of the network operating system in order to support underlying transmission media. Thank you.